Welcome you all. On today's session, I will explain about Parsons turbine. So these Parsons turbines also called as 50% of reaction turbine. Now there is one derivation related to 50% of axial flow reaction turbine. So that is, show that for an axial flow reaction turbine, the degree of reaction is given by R is equals to V of A by 2U into cot beta 2 minus cot beta 1, and also show that for axial flow 50% reaction turbine, the blade speed is given by U is equals to V of A cot beta 2 minus cot beta 1, where beta 1 and beta 2 are inlet and outlet rotor blade angles. Assume velocity of flow or axial velocity to be constant. That means the V of A at inlet and V of A2 at outlet to be same. The combined velocity diagram for an axial flow reaction turbine is as shown in figure 6.9. So according to this, here the V1 represents the absolute velocity to inlet and corresponding angle of their fixed blade is alpha 1, and relative velocity of blade at inlet is VR1 and corresponding angle is beta 1. And similarly, the relative velocity at outlet is given by VR2 and the corresponding angle is beta 2, and absolute velocity of fluid at outlet is V2 and corresponding angle is alpha 2. So according to the given data, the V of A1 at inlet is equals to V of A2 at outlet, and delta U represents the summation of the V of U1 as well as V of U2. So from this velocity triangle, we can take some relations, the trigonometric relations here. So in this one, say x1 distance is given. The x1 is equals to, if termed in trigonometric relations as, if you take cos beta 1 is equals to ratio of x1 by VR1. The cos beta 1 is equals to x1 by VR1. That means the x1 distance x1 is equals to VR1 cos beta 1. And one more relation is VU1. So if you take the alpha 1 angle, the alpha 1 relation, the alpha 1 is equals to VU1 to by V1. So that means now I want to take the distance of VU1 is equals to V1 cos alpha 1. So coming to the exit velocity triangle, so here x2 distance is taken as, if you take consider this velocity triangle, that is a cos beta 2 is equals to the ratio of x2 by VR2. That means the distance of x2 is equals to VR2 cos alpha 1, as well as VU2 is equals to the cos alpha 2 is taken, cos alpha 2 is equals to VU2 by V2. So with respect to that, VU2 is equals to V2 cos alpha 2. And here you can also take the distance of x1 is equals to the total length of V of U1 minus U. The one more expression is what? The x1 is equals to VU1 minus U. Similarly, in x2 is equals to the summation of U plus VU2. So these are the some trigonometric relations are considered while deriving the expression for this degree of reaction as well as blade speed U. So from data in a problem, the V of A1 is equals to V of A2, that is equals to V of A, because of flow velocity is constant from the inlet to the exit. So degree of reaction for axial flow turbine, the degree of reaction is given by the ratio of static head to total head. So because of this axial flow turbo machine, the blade velocity at inlet is equals to blade velocity at exit. For that reason, in this static head expression is taken as only half into VR2 square minus VR1 square, and total head is given by E. So that is equals to, and that 1 by 2 is then numerator, and that 2 is taken to denominator. Because of that, the degree of reaction R is equals to VR2 square minus VR1 square by 2 into E. From velocity diagram, VU1, V of 1, V of U1 plus VU2 is equals to x1 plus U plus x2 minus U. That is equals to what? That is a VU1 plus VU2 is equals to distance of x1 plus x2. The x1 is taken as V of A1 cot beta 1 plus V of A2 cot beta 2. So according to trigonometric relations, by considering that velocity triangles, the x1 distance is taken as V of A1 cot beta 1 and x2 distance is taken as V of A2 cot beta 2. Or VU1 plus VU2 is equals to, so here V of A1 is equals to V of A2 is equals to VA, because of flow velocity is constant. Now V of A is taken outside, common outside. So for that reason, this equation becomes VU1 plus VU2 is equals to V of A into cot beta 1 plus cot beta 2. From velocity diagram, sin beta 2 is equals to V of A2 by VR2. That means VR2 is equals to V of A2 by sin beta 2. So here the VR2 is equals to 1 by sin beta 2. 1 by sin beta 2 is here. The 1 by sin beta 2 is equals to cosec beta 2 and V of A. Similarly, sin beta 1 is taken here. The sin beta 1 relation is V of A1 by VR1. So for that reason, so VR1 is equals to V of A1 by sin beta 1. So once again that expression also same, VR1 is equals to V of A cosec beta 1. So these are the two expressions taken from the velocity diagram, that is a VR2 as well as VR1 expressions. Then energy transfer is equals to U into VU1 plus VU2. So that is equals to E. Energy transfer is equals to U into, say previously derived some expressions, that is a VU1 plus VU2 is VU2. In that one, the V of A is common, that is taken outside. The inside the bracket, that is cot beta 1 plus cot beta 2. And the VR2 square minus VR1 square. So already we derived one expression for VR2 as well as VR1. So now this VR2 square minus VR1 square expression is written as, that is equals to V of A square cosec square beta 2 minus V of A square cosec beta square cosec square beta 1. So here VR2 square minus VR1 square is equals to, so here once again V of A square is common, taken outside. The inside the bracket now cosec square beta 2 minus cosec square beta 1. Therefore degree of reaction is equals to, the degree of reaction is equals to the numerator, that is a VR square minus VR1 square. The expression for that VR2 square minus VR1 square is V of A square into cosec square beta 2 minus cosec square beta 1. And for energy transfer expression is, there is a denominator, there is a 2E, that is a 2 into energy energy transfer equation becomes now U into V of A cot beta 1 plus cot beta 2. So now here from the numerator there is a V of A square and the denominator V of A is there. So that will get cancelled. And one V of A get cancelled over here. So now V of A at the numerator. Now cos square beta 2 can be written as 1 plus cot square beta 2. So according to the trigonometric relations, so cosec square beta 1 can be written as 1 plus cot square beta 2. So once again here also same thing, minus cosec square beta 1 is there. You can write this cosec square as 1 plus cot square beta 1. And the denominator 2 into u cot beta 1 plus cot beta 2. So in this one, after that the degree of reaction R is equals to V of A. If you open up these brackets, say here 1 plus cot square beta 2, then in the second term minus 1, then minus plus, that is a minus cot square beta 2, then plus 1 as well as this minus 1 will get cancelled. The remaining terms at the numerator is V of A into cot square beta 2 minus cot square beta 1, and denominator is 2 into u cot beta 1 plus cot beta 2. So now in the numerator the cot square beta 2 minus cot square beta 1 is there. So that is in a form of a square minus b square. So according to the a square minus b square, we can expand that one as a plus b into a minus b. So according to that logic, the cot square beta 2 minus cot square beta 1 can be written as cot beta 2 minus cot beta 1 according to a minus b relation. Another one is a plus b, that is cot beta 2 plus cot beta 1, and denominator is 2 into u cot beta 1 plus cot beta 2. So now here cot beta 1 plus cot beta 2 at denominator, that will get cancelled with the cot beta 2 plus cot beta 1 in numerator. Afterwards the degree of reaction R is given by V of A by 2 into u and cot beta 2 minus cot beta 1. So now that expression is proved. That is what the degree of reaction R is equals to V of A by 2u cot beta 2 minus cot beta 1. For an axial flow 50% reaction turbine, for an axial flow 50% reaction turbine, degree of reaction R is equals to 0.5. Now substitute in the previous expression, the degree of reaction value is 0.5. So that is equals to half. We can write that 0.5 as a half. 1 by 2 is equals to V of A by 2u cot into cot beta 2 minus cot beta 1. So now rearrange this expression as in term of u. The 2, that is u is equals to V of A into cot beta 2 minus cot beta 1. So now one more expression as proved in that given derivation to prove that what blade velocity u is equals to V of A cot beta 2 minus cot beta 1. The alternate method for that one, from the velocity diagram, the u is equals to vu1 minus x1. We can write that one vu1 as v of a cot alpha 1 minus x1 as v of a cot beta 1. For an axial flow 50% reaction turbine, alpha 1 is equals to beta 2 and alpha 2 is equals to beta 1, and also V1 is equals to VR2 and V2 is equals to VR1. So these are the some assumptions are made for 50% of the reaction turbines. According to that 50% of the reaction turbine, alpha 1 is equals to beta 2 and alpha 2 is equals to beta 1. And also with respect to velocity, V1 is equals to VR2 and V2 is equals to VR1. And take these relations and assumptions and substitute the values in given expression u, that is u is equals to v of a into cot beta 2 minus cot beta 1. Now second derivation on that 50% of reaction turbine. For a 50% reaction steam turbine, show that alpha 1 is equals to beta 2 and alpha 2 is equals to beta 1, where alpha 1 and beta 1 are inlet angles of fixed and moving blades. Alpha 2 and beta 2 are the outlet angles of fixed and moving blades. The general equation of degree of reaction for axial flow reaction turbine is, already we derived this expression, degree of reaction R is equals to V of A by 2U into cot beta 2 minus cot beta 1. So now degree of reaction R is equals to V of A by 2U. Now here for the cot alpha 1 is added at one expression and is subtracted, that is a cot beta 2 minus cot alpha 1 plus into cot alpha 1 minus cot beta 1. From the velocity diagram of that given compound velocity diagram figure 6.9, u is equals to vu1 minus x1 and vu1 can be written as v of a1 cot alpha 1 minus x1 is equals to v of a1 cot beta 1. Assume velocity of flow or axial velocity to be constant, that is v of a1 is equals to v of a2 is equals to v of a, and u is equals to blade velocity is equals to v of a cot alpha 1 minus cot beta 1, or u by v of a is equals to cot alpha 1 minus cot beta 1. Then R is equals to v of a by 2u cot beta 2 minus cot alpha 1 plus u by v of a, and finally it is gets simplified and degree of reaction R is equals to 1 by 2 into v of a by u cot beta 2 minus cot alpha 1 plus of for 50% of reaction steam turbine R is equals to 1 by 2, therefore 0 is equals to cot beta 2 minus cot alpha 1 is equals to cot alpha 1 is equals to cot beta 2, or alpha 1 is equals to beta 2. From the velocity diagram 6.9, u is equals to x2 minus vu2, that is equals to v of a2 cot beta 2 minus v of a2 cot alpha 2. Assume velocity of flow or axial velocity to be constant, that is v of a1 is equals to v of a2 is equals to v of a, u is equals to v of a cot beta 2 minus cot alpha 2, then u is equals to v of a cot alpha 1 minus cot beta 1 is equals to v of a cot beta 2 minus cot alpha 2. But alpha 1 is equals to beta 2. Now v of a into cot beta 2 minus cot beta 1 is equals to v of a cot beta 2 minus cot alpha 2, that is cot beta 1 is equals to cot alpha 2. Therefore alpha 2 is equals to beta 1. From velocity diagram v 6.9, v of a is equals to v1 cos alpha 1, that is equals to vr2 cos beta 2, but alpha 1 is equals to beta 2, so now v1 is equals to vr2. The v of a is equals to v2 cos alpha 2 is equals to vr1 cos beta 1, but alpha 2 is equals to beta 1. Now v2 is equals to vr1. These relations show that velocity triangles at the inlet and outlet of the rotor of a 50% of reaction stage are symmetrical. move on to next derivation, that is the maximum blade efficiency of the 50% of axial flow reaction turbine. So what is mean by reaction surging? Prove that the maximum blade efficiency of persons or axial flow 50% reaction turbine is given by neta B max, that is a maximum blade efficiency, is equals to 2 into cos square alpha 1 by 1 plus cos square alpha 1. In reaction staging, the expansion of steam and enthalpy drop occurs both in fixed and moving blades. Due to the effect of continuous expansion during flow over the moving blades, the relative velocity of steam increases, that is VR2 greater than VR1. For 50% of axial flow reaction turbine, alpha 1 is equals to beta 2 and alpha 2 is equals to beta 1, and also V1 is equals to VR2 and V2 is equals to VR1. Then velocity triangles are symmetric. Now what is the work done by the person's turbine or 50% of reaction turbine? W is equals to U into delta V of U is equals to U into delta V of U is equals to VU1 plus VU2. From velocity diagram, W is equals to U into VU1 plus X2, the VU2 written as X2 minus U. So that is equals to U into V1 cos alpha 1, that is a VU1 is equals to, here VU1 can be written as V1 cos alpha 1 plus X2 is written as VR2 cos beta 2, X2 is written as VR2 cos beta 2 minus U. But alpha 1 is equals to beta 2 and V1 is equals to VR2. Then the work done expression becomes U into V1 cos alpha 1 plus V1 cos alpha 1 minus U. So that is equals to 2 into U into V of V1 cos alpha 1 and minus U square, because here V1 cos alpha 1 plus V1 cos alpha 1 is there. That is a 2 V1 cos alpha 1, that is multiplied with the outside, there is a U, that is a 2 into U into V1 cos alpha 1 minus U into minus U, that is a minus U square, or W is equals to V1 square, that is V1 square is divided and multiplied with this expression, that is V1 square, that is taken as 2 into U into V1 cos alpha 1 by V1 square minus U square by V1 square. But blade speed ratio phi is equals to what? U by V1. So according to that, W is equals to V1 square, inside the bracket 2 into U by V1 is that is a phi, and 1 V1 and 1 V1 square get cancelled. The remaining next is a 2 phi cos alpha 1 minus U square by V1 square is equals to phi square. This is speed ratio, square of the speed ratio. For reaction turbine, energy available to rotor inlet is given by the energy available to rotor inlet is half into V1 square minus half into VR1 square minus VR2 square. So this is expression for energy transfer in reaction turbines, because the pressure drop occurs both in fixed blade as well as moving blade. But V1 is equals to VR2. Now this energy transfer or energy available at the rotor inlet is equals to half into V1 square minus half into VR1 square minus V1 square. So that is equals to, after simplification of that, we are getting V1 square minus VR1 square by 2. From the velocity diagram, VR1 square is equals to V1 square plus U square minus 2U V1 cos alpha 1. So actually this expression is obtained according to the cosine rule. So according to the cosine rule, the V1 square is equals to V1 square plus U square minus 2U V1 cos alpha 1. Then Energy available at inlet, rotor inlet is equals to V1 square minus half V1 square plus U square minus 2U V1 cos alpha 1. Then energy available E of A is equals to half into V1 square plus 2U V1 cos alpha 1 minus U square, that is equals to V1 square by 2 plus there is a V1 square taken outside. Now 1 plus 2U V1 cos alpha 1 by V1 square minus U square by V1 square. The speed ratio is given by phi is equals to U by V1. According to that, the energy transfer or available is equals to E of A is equals to V1 square by 2, 1 plus 2 into 5 cos alpha 1 minus phi square. So actually here in this previous expression U by V, V1 by V1, that is get cancelled. The remaining U by V1, there is a phi here. For that reason 2 into U into phi cos alpha 1. So here U square by V1 square is there. For that reason it is a phi square. So blade efficiency of reaction turbine. So what about the blade efficiency? Blade efficiency is given by the ratio of work done by energy available. The work done expression is V1 square 2 phi cos alpha 1 minus phi square, and energy available at the rotor inlet is given by V1 square by 2 1 plus 2 phi cos alpha 1 minus phi square. Now blade efficiency is equals to the 2 here in the denominator, that 2 is taken to numerator, is 2 into 2 phi cos alpha 1 minus phi square denominator. Now here V1 square get cancelled, V1 square and V1 square get cancelled, that is 1 plus 2 phi cos alpha 1 minus phi square. Or the blade efficiency is taken as the 2 multiplied and subtracted on this numerator at that time, the 2 into 1 plus 2 phi cos alpha 1 minus phi square, and once again this 2 is subtracted here, minus 2, and denominator 1 plus 2 phi cos alpha 1 minus phi square. So after simplification of this, 2 minus 2 by 1 plus 2 phi cos alpha 1 minus phi square, so that is equals to 2 minus 2 into 1 plus 2 phi cos alpha 1 minus phi square, that is the power of minus 1. That means this denominator 1 plus 2 phi cos alpha 1 minus phi square, that is taken into numerator. For that reason its power is minus 1 now. For slope for maximum blade efficiency, for the maximum blade efficiency is obtained by differentiating this blade efficiency expression with the speed ratio is equals to 0. So now differentiating of that, d by d phi is equals to 2 into 2 minus 2 into 1 plus 2 phi cos alpha 1 minus phi square, the power of minus half is equals to 0. After differentiating of that, you will get the answer 2 into 1 plus 2 phi cos alpha 1 minus phi square, power of 2, there is a 2 into cos alpha 1 minus 2 phi is equals to 0, and 2 cos alpha 1 minus 2 phi is equals to 0, and phi optimum, the optimum speed ratio is equals to cos alpha 1. There is one more relation you obtained here, there is an optimum speed ratio is equals to cos alpha 1. So where phi is equals to cos alpha 1, the blade efficiency is maximum, therefore the maximum blade efficiency is given by 2 into 2 cos square alpha 1 minus cos square alpha 1 divided by 1 plus 2 cos square alpha 1 minus cos square alpha 1, and finally you are getting the expression as maximum blade efficiency is equals to 2 cos square alpha 1 by 1 plus cos square alpha 1. That means in this session we discussed about some derivations or some expressions related to 50% of the reaction turbine. So that is in an axial flow type of the turbo machine. So here we will obtain the expression for degree of reaction, and here we will obtain the relations for the blade velocity and blade efficiency, and finally we derived expression for maximum blade efficiency as well as optimum speed ratio. Thank you.